For homework, I'll probably ask you to additionally do the first excited state case. It's easy to understand how probabilities can come out a little bit funny from just our classical picture if we think to that potential well. So this represents the potential from that goes to infinity after or below 0 and after L. The lowest ground state is just a sign kx over pi let's see, pi L, x over L. So it's going to look like that, where the wavelength is approximately 2L. But the probability density is going to look a little bit more sharply peaked because it's the square. And if I think about only the first quarter of this region, well, the probability of this particle being between 0 and L over 2, that does look like a half, just eyeballing what that function looks like. But being within the first quarter, it's not going to be equal to a quarter because the wave function is so strongly peaked in the middle. In fact, if I asked a separate question, what's the probability of finding it in the middle half of this graph, it'll be significantly more than 50%. I could do the same, this is for the n equals 1 case. I could do the same for the n equals 2. This would be psi of x, whereas n equals 2 has a wavelength that actually equals L. We get the same wavelengths as we do in classical physics for waves on a string, clamps at both ends. But what will the norm squared of this function look like? Well, it's going to look something like that. In other words, it's positive everywhere, as it has to be, because I've squared something that goes through 0. And I want probabilities to be positive all the time. I don't want to have negative probabilities. So that does the right thing. And notice that it's quite peaked. So the probability is high over here or over here. And furthermore, the probability is exactly 0 right there. Classically, this poses problems to us because we would think if the particle is sometimes over here and it has to get over there, how is it that it can never spend any time in the middle? Well, that actually turns out to be okay in quantum mechanics because we have to kind of release our idea that the particle is moving around and ask how does it get from here to here, because to say that it started here and is moving this way means that we're going to be measuring both position and velocity in order to make that statement that it's starting from here and moving over there. That's kind of like saying we're going to measure both position and momentum, and we know that by the uncertainty principle that has limitations. Rather, we have to think of this probability distribution as something completely different. It is the probability map of our density of where we're going to find this particle anywhere along the x-axis. And so if I went and did an experiment and I popped out an electron from this box, where would I have found it? Well, it would be quite likely here. It would be quite unlikely there. It would be quite likely here again. And if it doesn't allow me to predict where I'm going to see this particle, but if I did see the particle, I could rationalize to you after the fact why you found it where you did. Or if you repeat that experiment 10,000 times and told me the results of where you found the particle in each of those 10,000 experiments, what I suspect you would find is that you would build up a little histogram. And it would look something like that. And then I could tell you, well, I expected you to get that histogram. I expected your histogram to follow that dotted curve given by the probability distribution. probability density for this wave function. So the nature of a quantum mechanical prediction then is either a statement of probability for where you will find a single electron, or it's a predictive curve for where you would find the electrons or particles in a box if you repeated the trial 10,000 times or 100,000 times, and you would make a prediction of where those particles distributions would be. Notice what happens in the large n limit. This is n equals 2 again, I should say. In the large n limit, I expect a probability distribution with a huge number of peaks like this. Notice the n equals 1 had one sort of peak, n equals 2 has 2, and n equals 3 would have 3, and so on. Well, n goes to infinity is going to have a huge number, and they're going to become incredibly closely spaced together. This is almost like the classical limit. Where the particle just has a uniform probability of it being anywhere along the box because we think of it as sloshing back and forth and not really spending any more time in one place than another. So this is a lot like Bohr's correspondence principle, where we recover an average statement in classical mechanics in the large n limit, or the limit that h bar goes to 0.